Hello, and welcome to Weapons of Math Instruction. Almost a year ago, I did a series of videos for Pi Day, which we all know is 314. Well, today is a lesser known but equally important mathematical holiday, E-Day. And all this week, I'll be doing a series of videos in celebration of this day. So in the first segment, I'll introduce this important number for all y'all. Then in the subsequent segments, we'll look at a couple real-world applications, namely exponential growth and decay. So what's E? E is Euler's number. Euler was a mathematician from the 18th century, and he was one of the greatest to ever do it. The approximate value of E is 2.71828, or if we round to the nearest tenth, 27. So now you know why today's E-Day. E, just like pi, is an irrational number, meaning that you can't express it as the ratio of two integers. And if you take enough math classes, you learn several definitions of E. The first definition that people encounter is from college algebra or pre-calculus. E is the number that this expression here approaches as n approaches infinity. So as n gets bigger and bigger and bigger, this guy gets closer and closer to E. And what they're doing there is they're sneaking in a limit on you, but they're just not calling it that. A limit is a concept from calculus. So in Calculus 1, we sharpen this definition up a little bit. E is the limit as n approaches infinity of this expression here. Later on in Calculus 1, when you learn how to do calculus with exponential and logarithmic functions, you learn that E is the unique number that satisfies this equation. So the integral from 1 to E of dx over x equals 1. And the integral of dx over x, that's the natural logarithm function. And if you're brave enough to go on to Calculus 2, you learn about infinite series, you find that E is given by this infinite sum here. It's the sum as n goes from 0 to infinity of 1 over n factorial. And I've listed out the first few terms here. Later on this week, I'll demonstrate the equivalence of these definitions so that we know that they all produce the same number. Okay, on to the second segment, exponential growth. The function f of x equals e to the x, so this is the exponential function with base e. It exhibits exponential growth. What does that mean? Well, here's the graph of f of x equals e to the x, and you can see that as x increases, that is, as we move to the right on the x-axis, the graph of this function shoots up very rapidly. That's exponential growth. The standard application of exponential growth that we teach in college algebra or pre-calculus courses is continuously compounded interest on an interest-bearing account. So P is the principal amount of money invested in the account, R is the annual interest rate, T is the number of years, and if the interest is compounded more than once per year, then N is the number of compounding periods. And this function A of T is the account balance at time T. We're going to work our way up to continuously compounded interest by looking at some simpler examples. So the simplest example of compounded interest is interest that's compounded annually. And the account balance at time t is given by this exponential function here. So it's the principal times 1 plus the interest rate raised to the power of t, the number of years. Now, if you compound more than once a year, say monthly, then we divide the interest rate by the number of periods, which is 12 months in a year, and we multiply t by 12 to get the total number of compounding periods over the life of the account. Suppose we compound even more frequently, say daily. So without worrying about leap years or anything like that, we'll divide the interest rate by 365 and multiply t up here in the exponent by 365. In general, if interest is compounded n times per year, this is the expression that gives you the account balance. So we divide the interest rate by n, and we multiply t by n up in the exponent. And the larger n is, the faster the account balance grows. So this raises an interesting question. What would the account balance look like if the interest were compounded infinitely often? That is, if it was compounded continuously. So this is the same thing as asking what would happen if n approaches infinity. So let's work it out. Using the language of limits from Calculus 1, the account balance under continuously compounded interest would be the limit as n goes to infinity of this exponential function. Now, to make the math a little more transparent so that e just kind of pops out of this naturally, I'm going to do a little change of variable. So I'm going to define a new variable, x, which is n over r. So that means that 1 over x equals r over n, which is this ratio you see right here. And n, the number of periods, equals x times r. So note, X is just n divided by r, and r is a constant. The interest rate is constant. So, if n goes to infinity, this implies that x goes to infinity as well. So I can rewrite the limit like this. I've taken p and pulled it outside the limit because you can do that with constants. And what we have is the limit as x goes to infinity, and this r over n becomes 1 over x, and the exponent becomes xrt. Now, taking advantage of properties of limits and exponents, I could rewrite this function like so, where I have the limit as x goes to infinity of 1 plus 1 over x to the x power inside, and I have the exponent rt outside. But if you'll recall from the first slide, this guy right here, this limit, that's e. So I can rewrite the account balance for continuously compounded interest as a of t equals p times e to the rt. Still with me? Good. The last segment is on exponential decay. So the function f of x equals e to the negative x exhibits this property called exponential decay. And what does that mean? Well, picture's worth 1,000 words. Here's the graph of f of x equals e to the negative x. And you can see that as x increases, that is, as we move to the right on the x-axis, the value of this function shrinks rapidly. It never quite gets to 0, but it does keep getting smaller. And the canonical application for exponential decay that we teach in math classes is radioactive decay. So you probably heard about radioactive decay at various times in your life. Carbon-14 dating, they also talk about it, when radon gas leaks up in your basement. So here we're going to dig into the mathematics of it a little bit. So I'm going to define some variables. So n sub 0 is the initial amount of radioactive substance that you have. And time 0 is just whenever you decide to start clocking the time. So when you hit the button on your stopwatch, that's time 0. R is a decay constant that governs how quickly the radioactive substance decays. And T is the number of years that the sample of the substance is left to sit there. And this function n of t is the amount of radioactive substance at time t. And the mathematical model is n of t equals n sub 0 e to the negative rt. So there's e again. Now, the decay constant r is typically not listed for a radioactive substance. Usually, instead, what's reported is something called the half-life, which is a term you may have heard. So I'm going to tell you all about it. The half-life, which I've denoted by this Greek letter tau, of a radioactive substance, it's the amount of time needed for a sample of that substance to decay to half of its initial amount. So, n of tau, if I plug the time tau into this function, all right, I get n sub 0 e to the negative r tau. By definition, that's one half of the initial amount, n sub 0. So that's a precise mathematical statement of this sentence written here. Now, if we focus on these two members of the equation, notice that n sub 0 appears on both sides. So we can divide it out to get this. E to the negative r tau equals 1/2. And what I'm going to do is express the decay constant in terms of tau. And I'm going to do this by taking the natural logarithm of both sides. So I take the natural log of e to the negative r tau, and over here I've rewritten 1/2 as 2 to the power of negative 1. And I've taken the natural log of that as well. Now, the natural logarithm is the logarithm in base e. And this is the exponential function in base e. And these two are inverse functions of each other. So when I take the natural log of e to the negative r tau, I just get the exponent. So on the left side, I get negative r tau. And on the right side, I use a property of logarithms that allows me to bring this exponent out front as a coefficient. So negative r tau equals negative natural log of 2. And what I'll do is I'll divide both sides by negative tau. And I got the decay constant in terms of tau. It's the natural log of 2 over the half-life. And the interesting fact here is that the half-life and the decay constant, they only depend on each other. They don't depend on the initial amount of radioactive substance that's present. So, thanks for hanging with me. I hope you found this first video interesting and informative. And I'll be back at you tomorrow with more nifty facts about E. Talk to you later. Hey everybody, if you enjoyed this video and want to see more like it, then please do follow me on my socials. You know you want to.